Hello again. Welcome to chapter 9 again. And this is the last section of chapter 9 that we would like to cover, which is actually the last section for the class. And it's an introduction to probability. Now, probability has another name. We call it the science of uncertainty. It's one of the areas of mathematics, along with statistics, that has a very wide application in real life, from politics to product reliability to medicine to manufacturing and even gambling. Obviously, if you are a good mathematician in the area of probability and statistics, you probably will do well if you go to Las Vegas and bet and gamble. Actually, the origin of probability, it's very shady. It started in the gambling houses of Western Europe in I would say middle of 16th century, about 500 years ago. Anyways, how do we define probability? We usually look for an event. So, for example, if I roll a die, I have six numbers on a die, right? So, what's the probability of, what is the chance, I should say first, of rolling a 2? There's only one 2 on the dice, on the die, right? So you have 1, 2, 3, 4, 5, 6. There are those six possibilities. What's the chance of rolling a 2? It would be 1 out of 6, right? Because there's only 1 2 in there. What's the probability of rolling a 5? Again, 1 out of 6. What's the probability of rolling an even number? 1, 2, 3 out of 6, or 1/2, and so forth. So this is your sample space that all the possibilities are defined. So we usually abbreviate probability as capital P, and the event we are looking for, let's say here, the event we are looking for is the rolling of a 2. So probability of an event is the number of desired outcomes over the total number of outcomes. So the number of desired outcomes over total number of outcomes. Now, probability is always a number between 0 and 1. You can define it as in percentages, in decimals, in fractions, but it's always between 0 and 1. A probability of a 0, that means the event is not going to happen. The probability of 1, that means the event will happen for certain. It's 100%, or anything in the middle. So, for example, if I say the probability of having rain tomorrow is 80%, that's between 0 and 1. Probability of sun rising tomorrow is 100%, or 1, hopefully. Otherwise, we won't have life. Okay, so that's how we define probability. So if I say what's the probability of rolling a 2, that's 1 out of 6. Number of desired outcome over the total number of outcomes. What's the probability of rolling a number that is greater than 2? So how many numbers are greater than 2? So 3, 4, 5, and 6. That's 4 out of the total number of outcomes, which is 6, which can be reduced to 2/3. Or you can change it into decimals or write it as fractions. Or what's, as I said, what's the probability of rolling an even number? We have 3 even numbers, which is 3 out of 6 or 1/2, or you can write it as 0.5, or you can write it as 50%. Doesn't matter. Fraction, decimal, percent. Oops, 50%, not 5%. Fraction, decimal, percent, doesn't matter. They all mean the same thing. But it's always a number between 0 and 1. Okay, so let's say a lot of times you might see probabilities with cards, playing cards. It's gambling. So what's the probability of the event of drawing a king in a deck of cards? Okay, how many kings do we have in a deck of 52 cards? We have 4 kings, 4 out of 52, which reduces to 1/13th. So that's the probability of drawing a king. Now, if you look at the figure on page 713, figure 9-9 on page 713, it gives you all the different types of cards. I'm not much of a card player, so I'm not too familiar with different suits or whatever they're called, and different types of cards. Okay. I want to look at example number 3. Let's take a look at that example at the bottom of page 713. It says a family of 5 has 2 girls and 3 boys whose ages are 21, 19, 15, 13, and 9. One is to be selected randomly. Find the probability that a teenager is chosen. So who are the teenagers? Obviously not 9 and 21, right? So it's 3 out of 5. It's 3 out of 5, or 0.6, or 60%. That's the probability of choosing a teenager. A 13-year-old, a 15-year-old, or a 19-year-old. Okie dokie. All right. So then let's talk about complement of, oops, sorry, I keep hitting the camera. Let's talk about complement of an event. What does that mean? Complement of an event. So for example, if I say there's a chance of rain, the chance of rain tomorrow is 20%. So what is the chance of not having rain tomorrow? That will be 80%, right? If 20% is a chance of having rain, then 80% is a chance of not having rain. So that is a complement of the first probability. So, and 80% and 20%, if you add them up, gives you 100%, or 1, right? So probability of an event can be defined as 1 minus its complement. Now the way we show complement is like that little squiggly line an event. So that's a complement of an event. So probability of having rain is the same as 1 minus the probability of not having rain. Because if you add a probability of an event to its complement, it should add up to 1. So if I move this to the other side, I'll get this. Okay? So based on that, let's look at example number 5 on top of page 715. Let's see. It's top of page 715. Let me bring it to you. It says use complementary events to answer the following questions. Okay, a single card is drawn from a well-defined deck. What is the probability that is not diamond? That is not diamond. So what's the probability of having a diamond? So look at it. Look what they wrote. It says, since there are 13 diamonds in a standard deck of cards, then the probability of complement of having a diamond, which means not having a diamond, is 1 minus the probability of having a diamond. What's the probability of drawing a diamond? That's 13 out of 52. Okay, which I can write as 52 over 52 for 1 minus 13 over 52, which gives me 39 over 52, which is 0.75 or 75%. So the probability of not drawing a diamond is 75% or 0.75. Okay. What's the probability? It says a single letter is picked at random from the letters in the word divisibility. What's the probability? Is not an I. So first of all, how many letters do we have? We have 1, 2, 3, 4, 5, 6, 7, 8, 10, 11, 12. We have 12 letters, right? Okay. So what's the probability that it's not an I? So what's the probability of having an I? So what's the probability of not having an I? Would be 1 minus the probability of having an I. And the probability of having an I would be 1, I forgot how many it was, 15? 1, 2, 3, 4, 5, 6, 7, 8, 10, 11, 12. Sorry, 12. And how many of them are I's? 1, 2, 3, 4, 5. So that will be 5 over 12. So that's 12 over 12 minus 5 over 12, which is 7 over 12, which would be 7 divided by 12 is 0.58 or 58%. Okay. All right, very good. Okay, so that was example 5. All right. Okay. Let's take a look at example 7. Okay. Now, before we get to example 7, I would like to point out this figure on page 715, the bottom of page 715. It says the chart in figure 9-10 shows all 36 possible outcomes from experiment of rolling 2 fair dice. So this is all the, so make sure you remember this page because you might need it for your homework or for a quiz or a test, this diagram, so you don't have to redraw it for yourself. Okay, so let's look at example 7. Example 7 is talking about, let me clear these guys. There we go, example 7. So example 7 is saying 2 fair dice are rolled. What is the probability? The sum of both dice is greater or equal to 5. So you want to find the probability that the sum is greater or equal to 5. So it might be easier, because you have so many different outcomes, to find the probability that the sum is less than or equal to 5 and then subtract it from 1. So basically you're doing the complement. First find the complement and then figure it out. Okay. So actually this should be just less than 5. Okay, so if you go back to this diagram, how many sums do we have that is less than 5? And it is drawn for you in this red area, because you can have 1 and 1, 1 and 2, 1 and 3, 2 and 1, 2 and 2, 1 and 3, right? 3 and 2 is 5, 2 and 3 is 5, and then the rest are all larger. So how many do we have? 1, 2, 3, 4, 5, 6. So the probability of having a sum being less than 5 is 6 out of 36. Okay, let's keep it that way. Let's not reduce it. But that's not what I want. I want the probability of having a sum that is greater or equal to 5. So all I do is subtract that from 1. So that's 36 over 36 for 1 minus 6 over 36. So that gives you 30 over 36, which reduces to 5/6. So that's the probability of getting a sum that is greater than or equal to 5 if you roll a pair of dice. Okay. Now, let's take a look at number 8. These are good examples, that's why I'm going over them. It says, actually, 8B. 8B is a better example, because you might see a problem, a homework problem like that. Of the 42 seniors at Jacobi High School, 23 are female and 19 are female. And 19 are male, sorry, I can't read. A group of 5 students is to be selected at random to attend a conference in Reno, Nevada. What is the probability the group will have exactly 3 females? Exactly 3 females. Okay, so this is a probability question, but at the same time, it's using combinations that we talked about earlier. So of 42 seniors, so there are 42 seniors, so we have 23 female, and we have 19 male. Okay, a group of 5 students is, and we have a total of 42, obviously. A group of 5 students is to be selected at random. Okay, so remember that what is the definition of probability? The number of desired events over the total number of events. Okay, so what's the total number of outcomes? That will be 42 students choosing 5. That's the denominator. That's the total number of outcomes. 42 students, we just want to choose 5 students out of them. But we have 23 students that are female, and our question is, what's the probability the group will have exactly 3 females? So if I choose 3 out of them, then the rest would be male, right? So since I'm sending 5 people, 3 of them are exactly female, then 2 of them have to be male. And we have that. And that's the desired number of desired outcomes over total number of outcomes, which gives you, if you do it on your calculator, it gives you 0.356 or 35.6%. The probability of choosing exactly 3 females student from this group of seniors. Okay, I'm going to stop right there and continue in the next video.